So a large number of people were shown a video of a collision between a moving car and a stopped car. Each person responded to how likely the driver of the moving car was at fault on a scale from 0, not at fault, to 10, completely at fault. The distribution rating under ordinary conditions follows a normal curve with a mean of 5.8 and a standard deviation of 0.8. Now, 16 randomly selected individuals are tested in a condition in which the wording of the question is changed to, quote, how likely is it that the driver of the car who crashed into the other was at fault? These 16 research participants gave a mean at fault rating of 6.3. Did the changed instructions significantly increase the rating of being at fault? So we're going to know, is this just due to random chance? If I picked another 16 people, there's going to be some variability within that. How likely is it that a result this extreme would occur just by chance? So part A. Okay, so we want to carry out the z-test using the 5 steps of hypothesis testing at the 0.05 level. So determine the research and null hypothesis. This is generally the first step when you're creating these. So it's often easier to come up with a null. So the null is a dull, that there is no change, that it's the mean is less than or equal to whatever we have here, because our research hypothesis, maybe the research hypothesis in this case is easier. We're wanting to know, did the changed instructions significantly increase the rating of being at fault? So I'm going to change my answer, what I said earlier, that it's probably easier to go ahead and do the research hypothesis. Okay, so the research hypothesis, B is the only one that has it where it increases, and the null is the opposite. So the null would be that it's the same or less than. So the next part, assume the distribution of means is approximately normal. What is or are the cutoff sample scores on the comparison distribution in which the null hypothesis should be rejected? So to find this cut score, we're going to go over here to StatCrunch, go to Stat, Calculators, and select Normal. And we're trying to find this z-score, and we'll put point. So we want top 5%, so it needs to be 0.95, right? So 95%. The shading will tell you. If you put in 0.05, which I know a lot of you would to begin with, you'd say, wait a second, I know it's got to be greater than, and so you change that to, wait a second, I got to put that 0.95. It's okay, easy to correct. So 1.64. I don't know how many places they want us to round. Let's check that out. Okay, it wants us to 2 places, so we'll put 1.64. This is a one-tail test, right? It's a directional, so we're not going to put in 2 values. Determine the sample's z-score on the comparison distribution. A couple different ways to do this. We can do it by hand, the way the book showed you. You find the standard error. The standard error is notated by sigma sub m, and it's just the standard deviation divided by the square root of n. So we take the standard deviation of 0.8 divided by the square root of 16, and we get 0.2. So that is the standard error. Then we use our z-score formula. And I believe instead of x bar, they may have used m in the text. So that's just the sample mean minus the population mean divided by the standard error. So you put those in and you get 2.5. So that is our cut score. Okay, as usual, we can do this directly in StatCrunch. So go up to Stat. This is a Z statistic, and it's one sample, and we're just given summary statistics. So our sample mean was 6.3. Standard deviation. Now we put in the standard deviation, the original standard deviation, which was 0.8. And the sample size was 16. And now we're performing a hypothesis test. And here the mean was 5.8. And recall, we want this, our research hypothesis, which is this HA, also called the alternative hypothesis. greater than. We don't want a confidence interval for this particular one. If we did, we would select that. Press compute. And we see our z statistic is 2.5. Here's our standard error, 0.2 that we got before. And then here is the p-value. The likelihood, the probability that we actually get a value this extreme given that it's the null is true. Now for StatCrunch, in most tests, the null is set up to be equals. You get the same thing if you change that to less than or equal to. So most programs just leave that at equals. So now we need to decide if we're going to reject or fail to reject the null hypothesis. Recall our cut score. So on a normal curve, our cut score was at 1.64. So if our z value ends up in this is called the rejection region, sometimes the critical region. If it ends up over here, then we reject it. And did it end up over there? Yes. Remember, it was 2.5. So our little guy, we'll put a little flag there, was at 2.5. So yes, we reject it. So let's look at our choices here. Sample score is extreme enough, so it's further. Remember, a cut score of 1.64 determines sort of how extreme is too extreme. Our sample score is extreme enough to reject the null hypothesis, and so that lends support to the research hypothesis. So C. Okay, so it says, let me go back and read it. Okay, it wants the general population in blue. Let me go ahead and sketch that out. So general population in blue, it's a nice normal curve, right? Comes back down. Centered here at our mean, which I believe was 5.8. It had a sigma of 0.8. Now the sampling distribution, the comparison distribution, so it's in black, and it's got a smaller standard deviation, right, at 0.2, and its mean was it 6.3? So shift it over just a little bit, and because our standard deviation was much smaller at 0.2, a fourth the size, more of the data is tightly clustered around the mean, so it's going to come up to a peak. Okay. So now we got to go over and pick the right one. Okay, it is C, only one that worked there. Explain your answer to someone who has never taken statistics before. Okay, the distribution of means uses many samples of the same size. So again, the sample distribution, you may have to refer back to your text on this. So it takes the sample size of 16 and goes through all of those it can, all the different possibilities, which with each sample randomly taken from the population of individuals, since the sample scores occur by chance 5% of the time or less. Remember, we're trying to get under that 5% threshold on the distribution of means. The results support the hypothesis that changing instruction significantly increases the rating at fault. Okay, one can be 95% confident that the true population mean is between blank and blank. Okay, we need to be able to figure the 95% confidence interval on the true population is between a lower bound and an upper bound. So how do we find these bounds? Recall the formula. Okay, so we find the upper and lower bounds of these intervals. So the upper bound is the sample mean plus 1.96. Remember, 1.96 came from the 95% confidence interval. You can switch over to the normal calculator app if you need to. So recall, you just put in the 0.05, it's 95%, so it's 0.05, and then divide it by 2. And you get the 1.96. So you put in the 0.2, which is the standard error, multiply that out, you get 6.69. Similarly, for the lower bound, it's a minus, and you're going to get 5.91. And so you put those in for the upper and lower bounds. Let me show you how to do this on StatCrunch. Okay, we've been here before, so we're going to go to Stat, ZStat, one sample with summary. You fill in all your stuff. Sample mean, 6.3. Standard deviation, 0.8. Our sample size was 16. And we're doing a confidence interval, 95%. And we get the same thing. We get a lower limit, 5.91, upper limit, 6. Okay, I know that was a long problem, so if you have any questions at all, please let me know. We did a lot of this one by hand to sort of develop the theoretical framework for this. Moving forward after this chapter, most of these will be done exclusively the way we did this one on StatCrunch. And I'll be honest, I don't care if you do these by hand or use them by StatCrunch. Either way is fine with me.